Welcome to the video lecture on the course op-amp and linear integrated circuit. In this session, we will be solving the problem related to a band pass filter. So take problem here. Design a wide band pass filter with lower cutoff frequency FL is equal to 400 Hz and higher cutoff frequency FH is equal to 2 kHz and pass band gain of 4. Draw the response of the filter and also calculate the Q factor or Q value of the filter. So here in this particular problem, we can divide this into three different parts. First is the designing a band pass filter. Second part is for drawing the frequency response, and the third part is for calculating the Q value. For designing the filter, the steps what we had followed for designing a low pass and high pass filter will be followed here. It is a combined effect what we have to follow. So first we will draw the circuit diagram of a wide band pass filter, and here we will be using a wide band pass filter with the low frequency and low filter and high pass filter, low pass filter and high pass filter. So this will be the circuit what we are going to use, and given FL is equal to 400 Hz, FH is equal to 2 kHz. Now seeing the circuit diagram, the first part is a high pass section. So we will design the circuit for a high pass filter. So for the high pass filter, the lower cutoff frequency is given as 400 Hz. First step is done. So lower cutoff frequency is selected. The second part is we have to select the value of the capacitance C. The capacitance C is equal to 0.05 microfarad, and using the expression of lower cutoff frequency FL is equal to 1 over 2 pi R into C, we can calculate the value of resistance by substituting the value of the lower cutoff frequency, which is 400 Hz, and the capacitance, which is 0.05 microfarad. We get the resistance value as 7.95 kilo ohms. So we have obtained the values of R and C. The next part is moving on to the low pass filter to find the values of R dash and C dash. For a low pass filter, the higher cutoff frequency is given as 2 kilohertz. We will choose a capacitance value C dash as 0.01 microfarad. So using the expression FH is equal to 1 over 2 pi R dash C dash, we get R dash as 7.95 kilo ohms. This is obtained by substituting value of FH, which is 2 kilohertz, and the capacitance 0.01 microfarad. So here we have obtained the RC components for the low pass as well as high pass cases. Next we have to obtain the value of R1 RF, R1 dash, RF dash. Here, as we know, the pass band gain AFT is nothing but AFT is equal to A1 A2. A1 is gain of high pass section, A2 is gain of low pass section. Given for us AFT is equal to 4. So what we will select here is we will take equal values for A1 and A2. So in this case, let A1 is equal to 2 and A2 is equal to 2. So which is equal to 2 into 2, which is equal to 4. So in this case now, since it is a non-inverting op amp, the gain of non-inverting op amp is 1 plus RF by R1. So which is nothing but A1 is equal to A2 is equal to 2. So while substituting this particular part here, we get the expression for RF and R1 are equal. So which indicates that RF is equal to R1 for both the sections. Therefore let RF, we will take it as 10 kilo ohm, therefore R1 is also equal to 10 kilo ohms. So with this particular part, we have completed the first part of the problem, that is the design part of the problem, with all these component parameters, the component values. The capacitance value whose C and C dash, R dash and R are equal, what we have obtained. RF and RF dash are equal, R1 and R1 dash are also equal. So this is the first part of the problem what we are obtained. Now moving on to the second part of the problem. For the second part of the problem, we have to plot the frequency response curve. To plot the frequency response curve, we have to deal with the expression transfer function expression, or magnitude of V0 by V. The frequency response, we will be using this particular expression, magnitude of V0 by Vin, which is equal to AFT f over fl divided by square root of 1 plus f over fh whole square times 1 plus f over fl whole square. So in this case, substituting the values of aft as 4, fl is 400 and fh is 2k, and since f is a variable, we have to follow this particular table. So in this case, varying the frequency in values of hertz, and we obtain the value of gain in decibel. So 20 log of V naught by V in. So once we have obtained this particular table, it will be easier for us to plot the response. So this will be the response varying from 10 to 10 kilohertz and further. So in this case, we can see, so between the range 400 to 2000, that is 400 hertz to 2 kilohertz, we get the bandwidth, where at 400 hertz the gain is minus 3 dB compared to the maximum value, and at 2 kilohertz the gain is minus 3 dB. Here maximum value is nothing but 10.42. So 10.42 minus 3 dB of minus 3 dB. So we will get nearly 8.84. So which is almost equal to that particular value. And this is how we obtain the frequency response of a band pass filter. And this is the second part of the problem. Moving on to the third part, to find the quality factor of the circuit. The quality factor Q is nothing but the center frequency Fc divided by bandwidth. Now, since it is a wide band pass filter, the center frequency Fc is given as square root of Fl times Fl into Fh. Substituting the values of Fl and Fh, we get center frequency as 894.427 Hz. Similarly, bandwidth Fh is equal to Fh minus bandwidth Bw is equal to Fh minus Fl. So substituting Fh and Fl, we get 1600, and substituting the values in quality factor expression, we get quality factor as 0.559. So this is the quality factor of a wide band pass filter. As we have seen, quality factor for wide band pass filter is lesser than 10. In this case, it is lesser than 1. So with this part, we have completed all the three parts of the problem: the design part, the frequency response, and finding the quality factor. So thank you for watching this video.